Alright, hey guys, we will go over the rest of the problems that you guys requested from that Google Forms. So we're just going to be going in order, starting with a worksheet. First up is 1, parts A through D. Okay, so we have an 85.2 gram copper bar heated to 221.3 degrees Celsius and placed in a coffee cup calorimeter containing 425 milliliters of water at 22.5 degrees Celsius. The final temperature of the water was recorded to be 26.1 degrees Celsius. How much heat was gained by the water? So heat, we're going to be solving for Q. So once more, we're using the equation Q equals mass times specific heat times delta T. Q is what we're solving for. Mass, since the density of water is 1 gram per milliliter, we have 425 grams of water times the specific heat of water, 4.184, and that's joules per grams Celsius or Kelvin. We'll use Celsius this time. And then times the change in temperature. The final temperature was 26.15, and the initial temperature was 22.55. Okay, so we'll plug in that difference there. I'm just gonna do delta T there because we're out of room to write that. If you plug this into your calculator, you should get Q equals 6,402 joules. Okay, so grams cancel, degrees Celsius cancel, we end up with joules. It's about 6,402 joules, and that is what's gained by the water, so that's why it is positive. Part 1b, how much heat was lost by the copper? So since Q gained is going to be equal to Q lost, Part B is going to be the same thing, 6,402 joules, but since it's lost, the sign for this is going to be negative. Okay. Part C asks, what is the specific heat of copper? So, we're going to be using the same equation, but this time we are solving for C. So we're going to have C being equal to Q divided by M delta T. So that's going to be C, so the heat of copper, is equal to Q negative 6,402 joules divided by our grams of copper, which is 85.2 grams, times 26.15 minus, this time the initial temperature isn't 22.55 degrees Celsius, it's 221.32 degrees Celsius. That's degrees Celsius, that's degrees Celsius. So then our unit for this, of course, is going to be joules over grams Celsius. So that means C, once you plug this into your calculator, is equal to 0.385 joules per gram degrees Celsius. Okay, so that's part C. Part D asks, was energy conserved in the process, and justify your answer. So yes, energy was conserved in the process. The heat lost by the copper, negative 6,402 joules, is equal to the heat in magnitude gained by the water. So yes, heat was conserved in this reaction. So that is number 1. Next we have number 3, part A and B. Okay. So number 3, a coffee cup calorimeter contains 100 mils of 1.5 molar barium nitrate at 25 degrees Celsius. A student pours 100 milliliters of 1.5 molar sodium sulfate at 25 degrees Celsius in the calorimeter. A precipitate forms and the temperature rises 29.7 degrees Celsius. So that no heat was lost to surroundings, volumes are additive, specific heat is equal to that of water, and the density is 1 gram per mole. Part A asks, this reaction could be represented as a complete ionic or net ionic equation. Write the balanced chemical equation that should be used in association with the change in enthalpy of the reaction for this reaction. Justify your choice. So part 3, what we are looking at is we have 2 aqueous solutions. The first is barium nitrate. Just put A there to save a little bit of room. And the second is sodium sulfate. Okay, so those are 2 reactants. They're both aqueous, and then we end up with 2 products. Arrow. You can kind of think of it as a simple double displacement reaction. So we're going to have 2 sodium nitrate. I know that because both of these have a subscript of 2, so to be balanced in the overall equation, we will have a coefficient of 2. And then the other thing we'll get is barium, BaSO4, barium sulfate. Now it says in the problem that 1 solid precipitate forms, so we have to decide which one of these is soluble, which is insoluble. This one stands out to me because sodium is in it. So sodium is always soluble, so we know this one's going to be aqueous. That means our barium sulfate is going to be the precipitate. Okay, so that means sodium is aqueous on both sides of the equation, so I'm going to knock that out. Nitrate is aqueous on both sides of the equation, so I'm going to knock that out. And then my overall net ionic equation would be Ba plus 2 plus SO4 2 minus yields barium sulfate solid. And we can add aqueous here. So this is a net ionic equation. So the question really asks, like, which equation do we show? We're going to show this overall reaction because this is what actually happens. So it's kind of like the spectator ions. They're part of the surroundings, not part of the system. Remember, the system only includes things that are included when the chemical reaction occurs. And there's kind of a glare there, sorry. There we go, now you can read it. So since the net ionic equation, that includes the systems, the overall, the nitrate and sodium, those are part of the surroundings, so the enthalpy of the reaction only is in regards to the system, really. So this is all we're worried about in terms of the overall enthalpy change during the reaction. So that's part A. Part B, here. Okay. Part B, find the amount of heat that was lost or gained by the solution in the calorimeter. Remember, the solution is the system, okay? So we are going to have, again, Q equals mc delta T. We're solving for Q. The mass, remember, it said to assume that the density of the solution is 1 gram per milliliter. So our grams of the solution is going to be 200 grams from the 100 milliliters that we added together. And then the specific heat is going to be equal to that of water, 4.184 joules per gram Celsius. And then our delta T, we said the final temperature was 29.7. The initial temperature was 25 degrees Celsius. Okay, so we plug this into our calculator, 200 times 4.184 times 29.7 minus 25, so times 4.7. You should get Q equals 3,933 joules. Okay, since the temperature increased, that means that the system lost heat. So it put heat out to the surroundings. That's why there was a temperature increase of the water. So really 3,933 joules were released by the solution. So since the water temperature increased, that energy came from the system, the overall reaction that occurred. So technically, that would make the Q, you can think of it as negative, or you can just say that this much was released, whereas this much positive was gained by the water. So you can say released or negative 3,933 joules. Okay, so that's part 3B. Then we had a question on number 4. The specific heat capacity of copper is 0.385 joules per gram Kelvin. If 353 joules of heat are added to 3.6 moles of copper at 283 Kelvin, what's the final temperature of the sample of copper? Okay, so I'm going to erase my work again. Hopefully you saw this. I don't know if I stood in front of it too much, but you can pause that and get that down if you didn't. I'll leave the equation on the board since we're going to be using it again anyway. So for number 4, we're given the number of moles of copper that we have, which is 3.6. So it's 3.6 moles. Since mass is in grams, I'm going to go ahead and use molar mass to convert moles to grams. So I am going to multiply by the molar mass of copper, 63.546 grams over 1 mole. Okay, so again, I'll move that so you can kind of read it. So if I plug this into my calculator, I find out that I have 228.77 grams of copper. So that's what I'm plugging in for my mass. And we're looking for the final temperature. So I'm going to put 228.77 grams. Then I'm going to put the specific heat of copper, 0.385. I'm going to go ahead and chop off units for now. I know that's not great, but just to save some room. And then what we're looking for is the final temperature. Remember, delta T is final minus initial, so I'm going to have T final minus the initial temperature, which is 283 Kelvin. And again, that's Kelvin, but kind of out of room on my board. Okay. Then, if you look at the problem, it tells you the heat that was added. So it tells you that you added 353 joules of heat. So we can plug that in for Q over here, 353. And that's in joules. So you can rearrange this equation to solve for the final temperature. Basically, you're going to have 353 divided by 228.77 times 0.385. And then plus 283. So if you plug that into your calculator, your final temperature that you have is going to be 287 K. Okay. So it should be 287 Kelvin for the final temperature for number 4. Okay. Then we have 5 part B. So specific heat capacity of iron is 0.45 joules per gram Kelvin. If I'm going to go ahead and stop this video because we only have 45 seconds, so I'll make another video for number 5 and beyond.